Hello, this is Professor Arai in section 6.4, Difference in Means. For this section, we will follow the same order that we've been using throughout this chapter. First, we will talk about the shape of the distribution, then we will talk about the confidence interval, and we'll finish the section by talking about the hypothesis test. So first, we will start with the distribution of difference in means. And for that, we have to introduce the new formula for the standard error. So the standard error for difference in means will follow this format. It will be the square root of standard deviation of the first population squared divided by the first sample size plus the standard deviation of the second population squared divided by the second sample size. So make sure you write it down. And as always, the larger the sample sizes, the smaller the standard error. The central limit theorem for difference in means states that if both sample sizes are sufficiently large, then I can look at this distribution as a normal distribution that is centered at the difference in means and that has a standard deviation that is equal to the new standard error. The new criteria is that both n1 and n2 need to be larger than 30. So let's see an example. Example 1. The average math SAT score for males is 534 with a standard deviation of 118. The average math SAT score for females is 500 with a standard deviation of 112. If we were to take random samples of 50 males and 50 females, find the distribution for the difference in means x bar m minus x bar f. So we need to use this order, males minus females. Now, before we start, we look at the sample size for the males and the sample size for females. Both of them are larger than 30. So I can look at this distribution as a normal distribution. And I need to state the shape, the center, and the standard deviation. I can do that using a sentence, or I can use the mathematical notation that we've learned. In both cases, I need to find the standard error first. And for the standard error, since I have difference in means, I'll apply the new formula. So it'll be the square root of the first population standard deviation squared over the first sample size plus the second standard deviation squared over the second sample size. So if you plug in all these numbers, you'll have the standard error to be at 23. The center will be the difference in means. You have the males minus the females. So you'll do 534 minus 500, and that will be 34. So you can describe this distribution by writing this mathematical notation. The way we read this mathematical notation is that this distribution is a normal distribution, looks like a bell-shaped, centered at 34, and has a standard deviation of 23. Previously in section 6.2, we said that in most cases we don't have the population standard deviation. And when we don't have the sigma, we will use S instead. However, replacing sigma with an S will have two consequences. First, instead of having the standard error, we will have an estimation of the standard error. And instead of using the normal distribution, we will be using the t-distribution. The same situation will happen in this section. If we replace sigma 1 and sigma 2 with an S1 and S2, the new formula for the standard error will be an estimation of the square root of S1 squared over N1 plus S2 squared over N2. Also, replacing sigma 1 and sigma 2 with S1 and S2 changes the distribution of the standardized test from normal to a t-distribution. So instead of z, you'll use t, and instead of the normal distribution, we will be using the t-distribution. The new thing in this section is that we have two sample sizes, so we have 2 degrees of freedom. We will only use the smaller one. So you will find n1 minus 1 and n2 minus 1, and then you'll take the smaller one and you'll enter that as a degree of freedom for that t-distribution. The second portion of this section is called the confidence interval for a difference in means. We still have the same formula for the standard error, so we will follow the same structure. However, instead of using z star, we will be using a t star. So again, every time you have a single mean or two means, we will be using this format. So the confidence interval formula will still take the same structure. It will be statistic plus or minus. Again, instead of z star, we will use t star times se. So if you want to write it down, make sure you write down this formula. This is the statistic, which is difference in means, plus or minus t star times the new formula for the standard error. Keep in mind that both sample sizes need to be larger than 30. Let's see an example. Example 2. 210 first-year college students were randomly assigned roommates. For the 78 students assigned to roommates who brought a video game to college, average GPA after the first semester was 2.84, with standard deviation of 0.669. For the rest, which are the 132 students assigned to roommates who did not bring a video game to college, average GPA after the first semester was 3.105. with a standard deviation of 0.625. The question is, how much does getting assigned a roommate who brings a video game to college affect your first semester GPA? Basically, we are looking for the confidence interval. Specifically, they asked me to find the 90% confidence interval. So for the 90% confidence interval, what do I need? I need the sample statistic, which is difference in average, and I have that. This number and this number. I need the standard error, and I can find that because I'm given the standard deviation S1 and S2. I'm also given the sample sizes. And I need the t star using the degree of freedom of the smaller one. So let's do this. So first, let's check the conditions. Both N1 and N2 are larger than 30, so I can go ahead and use my formulas. Second, I need to find the t star. Now, you will look at both sample sizes and you will, if you take 78 minus 1 and 132 minus 1, obviously this is smaller. So this would be the degree of freedom. So in this case, the degree of freedom will be 77. And I'm using a 90% confidence interval. So the t star will be 1.665. Let's see this on StatKey. So on StatKey, you will go again to t-distribution. You will enter the degree of freedom of 77. We are looking at the 90% confidence interval. Confidence interval is always two-tail. Change the midsection to 90 or 0.90. And you will see the t stars. So the t stars are the 1.665 and negative 1.665. So let's go back. So as we've seen, t star will be the 1.665. Next, we will calculate the statistic. So you have the first average minus the second average. So again, they didn't specify which one I should go first, but I can use any order and then follow that with my interpretation. And I'll show you what do I mean in a second. So the difference in mean in this case is negative 0.265. Fourth step is finding the standard error using the new formula. So you'll have to apply the standard deviation of the first group over the sample size of the first group. Obviously, you'll square the standard deviation first, then you divide by the sample size. And you'll do the same in the second fraction, add them up, and then take the square root. So you have the standard error equals 0.093. Now we start calculating the confidence interval. So the formula says it's the statistic, which we found, plus or minus. Again, we have plus or minus because we have two values for t's. So plus or minus the t star, you plug in there, and times the standard error. And we will find that the confidence interval is between negative 0.42 and negative 0.11. So we will say we are 90% confident that getting assigned a roommate who brings a video game to college decreases the mean first semester GPA by 0.11 to 0.42 points. So because we use the average of the roommates with the video games first, the values were negative, and in my interpretation, I made sure to explain that negative value by saying that the GPA went down. If you've used x2 minus x1, then you would say that the people who were assigned roommates without the video game did better than the people who assigned people with the video games. So in both cases, you are explaining the same situation, but in different words. The hypothesis test always assumes that the null is true. So the standardized test value will be statistic minus null over SE. So the new formula will be T equals statistic minus the null. The null is mu1 minus mu2 equals 0. So it will be minus 0, but we don't have to write it down. Over the standard error. We will keep the same criteria. Both sample sizes need to be larger than 30. And we will take the smaller value of the degree of freedom. So let's see an example. Example 3. The Pygmalion effect states that the greater the expectation placed upon people, the better they perform. Teachers were told that certain children were expected to be geniuses based on the Harvard test of inflected acquisition, a test that did not actually exist. The response variable is the change in IQ over the course of 1 year. So here's the data. You have the controlled group and the genius group. Obviously, these students are random, but the teachers were told that they were geniuses. You have the sample sizes. You have the difference in IQs after 1 year for both groups, and you have the standard deviation for both groups. Is there evidence that the Pygmalion effect exists? So since I need to find an evidence, I need to perform the hypothesis testing formulas. So first we need to state the hypothesis. The null will say that there is no difference. Both averages are equal. The alternative will say that the average of the genius group is larger than the average of the controlled group. Then we need to check the conditions. Both groups are larger than 30, so I can go ahead and use my formula. Then I would calculate the statistic, and calculating the statistic means finding the difference in means. So you have the difference in means is 3.8. The standard error, you will apply the new formula. So you'll have 13.3 squared divided by 65 plus 12 squared divided by 255, and you'll have the standard error equals to 1.813. Once you have the statistic and the standard error, you can go ahead and find T. And T is the statistic minus the null is 0, divided by the standard error. So T is 2.096. Once you have the T value, then you'll go and find the P value using StatKey. Keep in mind we will be using the smaller degree of freedom. So in this case, our degree of freedom will be 64. And this is a right tail test. So let's do this. So you'll go on T, degree of freedom 64, right tail test, and you will go beyond the T value. The p-value from the graph will be 0.02. So let's go back. So the last step is to compare the p-value to alpha. P-value here is smaller than alpha. Then I will reject the null and say that we have evidence that positive teacher expectations significantly increase the IQ scores on average in elementary school children. This experiment was published, and I just want to show you the line that described the p-value. This is the line that showed the p-value. It says the difference in gains could be ascribed to chance about 2 in 100 times, because our p-value was 2 out of 100. And so this is how you would see the p-value described in these journals. So in summary, the standard error in difference in means is given in this formula. The confidence interval for difference in means will be the statistic, which is difference in means, plus or minus t stars times the standard error. We will have 2 degrees of freedom, but we will take the smaller one. And this test statistic for difference in means will follow this following formula, which is t equals x1 minus x2 over the standard error. And that's it for 6.4. Thank you.